Hi, everybody, and thank you for joining us today for our AIA certified webinar, Walls at Work. My name is Kim Melton, and I will be the moderator for today's presentation. Before we dive into introductions, I would like to go over a few logistics. We will conclude the webinar with a live Q&A session, and if you have any questions throughout the presentation, you can submit them via the Q&A box to the right of your screen. Now, if you don't see the Q&A box, simply click on the Q&A in the top right corner, and that'll open the dialog box. Now, if you don't have Q&A in the top right corner, what you can actually do is if you hover over the center of your screen, you'll see a series of circular icons across the bottom. The second one from the right is an ellipsis. Now, if you click on that, it'll open the Q&A, and that'll open the dialog box that you can use to submit your questions, and we will answer those at the end. Also, we're going to follow today's webinar with a survey, and this is your opportunity to provide us with feedback on how we did today, ask any additional questions that you might have about the topic, or even suggest new topics for future webinars that you'd like to hear. This survey is part of how we deliver the JM experience to you. Now, the JM experience is actually based on 4 pillars of the JM culture, and those are listed there in the bottom left corner, and that's people, passion, perform, and protect. And these 4 cultures are part of the basis of how we do business here at Johns Manville. And your feedback is actually a key component to helping us better meet your needs. And so delivering on this JM experience is part of is understanding your feedback and implementing that to evolve to do better. So if you have any comments or suggestions as to how we can better accomplish this, or even if you feel like we've missed the mark today, we'd encourage you to fill out the survey and use your feedback we'll use your feedback to improve our future webinars and provide the information that has the most value to you. A final quick note here, this webinar is for educational purposes only, and it shouldn't be used as a substitute for professional engineering design, consultation, or documentation that might be required by the building codes, contracts, or applicable laws. So if you have any questions after the webinar, you can refer to our specific application guidelines and instructions, and those are located in the product sections of our website. Also, we're frequently asked whether or not we send out these presentations upon their conclusion, and while we don't send out the presentation itself, we do post a recording of it online for you to watch at your leisure or share with your colleagues. So this ensures that you have the presentation within its full context, and we will send an email to you when it's available on our site to watch on demand. So with that, I'm going to turn it over to Dwight to introduce himself and walk us through Walls at Work.
Hello, everyone. My name is Dwight Stone. I'll be presenting today. I've been with Johns Manville for about 5 years now. I actually just crossed the line of 5 years this year. And my background is primarily, no one has ever accused me of being a professional engineer. My background is actually in architecture. I started in 1995 as an architect in working in regional firms in the Denver area, and have worked in a number of firms on pretty much every different project type. And over time, I began to evolve into, my interest began to evolve into more quality control. And so I gravitated towards the specification side, opened up my own firm and ran that for about 10 years until I joined Johns Manville in 2015. So seen the gamut of different types of project types and different types of specification challenges. So I look forward to sharing some of that experience with you today as a building enclosure specialist. This is an AIA approved presentation, approved for learning units and health, safety, and welfare. So we will be reporting these credits to the AIA at the end of the presentation. So our learning objectives today are as follows. We're going to explore the concept of building envelope and wall design, how it relates specifically to the vertical elements, the walls. It is incorporated in the roof design as well and foundation design, but we'll look at how it relates to perhaps the most complicated element, which is the walls. We'll talk about the different environmental challenges that are going to try to prevent the optimal performance of these materials and systems, and then talk about how to mitigate the effects of heat, water, and air movement through these walls. At the end of the presentation, we'll look briefly into the concepts around fire performance and acoustic performance of these wall systems as well, both internal and external to the building. So let's discuss briefly what we're defining as the building enclosure. The building enclosure itself is, of course, this blue line, which moves around the building right here. which includes the roof system, insulation systems, wall systems, structure, and of course the foundation, whether it be a crawl space or a slab. So all of these elements, of course, need to work together, and tying them together it will result in the maximum performance of your system. So what are the elements we're trying to contain and resist? Of course, we're trying to keep conditioned space. It's not always warm. We're not always trying to keep it warm on the inside. Sometimes with cold storage, you're trying to keep it cold on the inside and it's warm outside. So these temperature variables can invert, but either way, we need to address the elements of water, precipitation, vapor, air, heat, sound, and fire with these wall systems. And so let's talk about how we address these effectively with the systems that we are going to design. So starting with a little bit of history, a little bit of background about the wall system itself. You see in the lower left-hand corner here, this is a mass wall. But these are still used today in some extent, not necessarily as the structure of an Irish church like this was 1,000 years ago. You wonder about the comfort, the livability of the space inside. Certainly have difficulty getting light into a system like that. And is it actually a wall or is it a roof? You know how you have moisture drainage issues which may occur, and also comfort and warmth on the inside. But you can't argue that it's not durable. It's lasted over 1,000 years now and will continue to last into the future. The evolution of that sort of mass wall system was the cavity wall, which still has elements of a mass wall being built of masonry materials tied together. And then you have the introduction in the middle here of this cavity. What is this cavity doing? Well, it separates the utility of the exterior and the interior wall space. The interior wall, of course, is a finished material at the inside. The movement of heat through this is slow. But in cold environments, the cold will translate to the inside, and in warm environments, it will also move through the mass systems. The separator here being this cavity. This cavity allows for airspace, insulation space, vapor movement, and basically separation of this exterior from the interior. With the evolution to framing systems, wood framing being the first and perhaps the easiest system to start with, you do have limitations on the height, of course, and the structure of the studs, but the studs themselves do have R value. So the standard 2x4 wood stud has an R value of about 4. The spaces in between are where the insulation, of course, goes, and the studs themselves function as structure and for multiple elements. When this structure gravitated towards steel, which has higher load capabilities, steel frame with steel infill, you're introducing an element into that structure which is no longer has resistive value. It's more of a conductor, and so you had at that point you were introducing elements which were compromising the thermal characteristics of those walls. So you can put insulation into the stud cavities, but at the same time, it's being defeated or flanked by these structural elements. So, which leads to today's designs or details of typical designs of wall systems today. Starting the left-hand side, you have the foundation system, how it meets the ground. You have an exterior continuous insulation interrupted only briefly by this concrete wall, which has some R value to it. The insulation is continued up the wall here and then inside the wall cavities as well. So you have exterior insulation moving around the building, also vapor retarders, which are eliminating movement of vapor, or at least slowing the movement of vapor within through these systems. In the center detail, you have a standard cavity wall system with a CMU backup and then a masonry veneer on the outside. The veneer is functioning as a rain screen in this condition, and then the continuous insulation is moving the dew point to the outside of that wall system, and then the structural backup is offering more additional masonry structure. This is a very thick, a very so portentous system, and a lot of systems use structural steel as a backup member, or sometimes wood framing as well. In the right-hand side, we see sort of a critical area of the current detailing. You have a roof system as it ties into the wall system, and how this is treated from a vapor and external continuous insulation perspective is important. Sometimes you'll see a spray foam detail which basically provides a vapor seal at this joint between wall and ceiling. Roof systems were the original exterior continuous insulation because the insulation is placed on the outside of the building envelope, at least for low slope systems. And you'll see sometimes this exterior CI continuing up the parapet and around and outside the walls. So to review, we looked at basically the function of the building envelope is separating that interior conditioned space from the external environment, which likes to move around in terms of thermal characteristics as well as vapor characteristics during the year. How it includes windows, roofs, foundations, wall systems, and the details that we're focusing on. And then how these designs affect the movement of air, heat, water, fire, and sound. How detailing is important to make sure that these elements are controlled, and the complexity of some of these systems and the evolution of the requirements. So let's look a little bit more closely into one of the primary aspects of a wall system, and that is water control. Water is the most damaging element, the primary element to control in a structure, from the roof system all the way down the walls and into the subgrade. Bulk water has the ability to move through substances through either leaks, capillary forces, or absorption of materials, and then as airborne through vapor intrusion with movement of air. And that could be simply through diffusion of vapor through a drywall board, or through intrusion with unsealed openings in the systems themselves. This can be amongst the most damaging elements, causing long-term damage over time. Moisture accumulation can build up inside of these wall systems and cause problems which cannot be seen immediately. So one of the critical aspects of bulk water performance is really requiring the wall system and roof system to work together to provide a continuous drainage plane. You see here the arrows moving from the roof, where of course gravity is bringing your rain down into your gutter system, gravity controlled down to the ground and away from the building, and then water. Frequently, a drip edge would be required in a situation like this to keep water from draining back, because it has tenacity to actually move back along these soffit areas. So the rain screen here is detailed, and then the water evacuation with a gap down below here and a drip edge being provided to keep water moving away from the face of the building. Wind is going to provide pressure to push that water into the building and try to prevent some of this activity. But the detailing required will actually keep the water moving in the right direction. These window systems, of course, will need to have proper flashing, through wall flashing, to keep the water moving out and away from the building. And then here, you have another gap being provided at the base, the connection to the foundation. So this movement of water is predicated on having materials that are water tolerant, so they don't break down with exposure to water. And then, of course, water repellent, so they don't wick water from one side of the building to the other side of the wall. Of course, having an air gap is important, having the right size air gap and making sure it doesn't get clogged or plugged to allow the water out, and integrate those flashings with the materials on the building. On the right side here, we see a sort of a visual list of all the areas that should be detailed properly at some point in your documentation to make sure that these areas are not compromised and water is draining away from the building. So on the left here, we see an older building that is, although it may not have had too many limitations on the budget requirements, was very well detailed and, of course, well built. It's also well maintained over time. So you see from the roof system all the way down to the cornice here, you see a drainage plane being defined and drip edges being pulling the water away from the face of the building. Here's another cornice, which allows for shelter to some extent, or the movement of water away from the face of the stone. You don't see any discoloration of the stone, which indicates there's no areas where water is pooling or tracking backwards to the facade of the building. You also see these windows inset, so they're pulled away, and the water keeps moving away from the glass. Even water that's sheeting down the glass will be moved away from the building out to a drip edge. And so you see the movement of water away from the facade down to the ground. In the center of the screen here, we see, let's say, a more cost-constrained structure, which has an opening here for light to enter into the window, and with light, you also get wet water damage. So this is obviously an area where there's a lot of rain, and the water will drip directly off of this overhang, this truncated overhang over the window system, and falls directly onto this window sill. And unfortunately, at that point, it's not draining away quickly enough, or it is not drying up quickly enough, and it actually tracked back into underneath the windowsill and required remediation of mold on the studs as well as of the insulation inside. So this was a problem waiting to happen because it's not designed correctly for the environment it's in. On the right-hand side, we see a building with multiple systems, sort of a more modern, approach to building design and a modern challenge. You see the brick veneer or stone veneer system here, and then meeting the glazed system, the curtain wall system up here, and then the other sort of element on the right-hand side. So where all these systems interconnect is where details, of course, need to be designed specifically to preclude water intrusion. Water can track back to windows, up window heads here, and then down along the window system, and then out along the base. So making sure that water moves away, making sure those systems are integrated is the challenge of this type of building. So let's shift gears here and talk about not bulk water resistance, but more vapor control. This is a psychrometric chart, difficult word to say, which indicates a couple of things. One is the concept of relative humidity to absolute humidity. So given a certain volume of air, the absolute humidity is the amount of bulk water contained as vapor in that amount of air. So let's say at 60 degrees, you have 80% relative humidity, which would mean this amount of bulk water contained in that air. If the temperature drops about 10 degrees, that water would condense and it would become 100% relative humidity with the same amount of absolute absolute humidity. So the movement of temperature, the sort of the dialogue of temperature and humidity or vapor is what this chart represents. Obviously, 40 degrees will hold less water than an 80-degree temperature. So this is a different graphic communicating the same idea. Here we have the pounds of water, which is the absolute humidity or absolute water content. At 40 degrees, the water droplets inside this volume of air are fairly close together, which indicates it's 50% relative humidity. With an increase of temperature, still it's 1 pound of dry air. 60-degree temperature, you see more space between the molecules of air, the air being lighter, as we call it. With the same amount of water would result in a 26% relative humidity. Increasing that even more, another 20 degrees, still 1 pound of dry air, same amount of water would result in 12% relative humidity. So how does that function in a building envelope? Well, you see here a typical environment where you're maintaining a 70-degree interior temperature and about a 40% relative humidity. This is a good comfort index for doing customary activities inside a building. Outside, we see a colder temperature and a 70% relative humidity. So what is the vapor movement going to be within this wall? Usually it's from warm to cold or higher humidity to lower humidity because they're trying to basically average out. So this interior temperature and relative humidity is diffusing through the drywall, the paint and drywall system here, into the wall system, and you can see what's going to happen when it reaches the point where it condenses, which would be where the temperature is cooling down to the point of saturation. It will condense on the backside of the exterior sheathing material. So it looks like this is a wood product. If it's a typical OSB is an absorptive product and will absorb and expand, and this may cause problems with both the structure as well as the integrity of the material over time. So in 30 days, with these parameters, about 0.07 pounds per square foot of water will move through this wall. So let's look at how air exfiltration would also contribute to this challenge. The vapor movement would be even more dramatic. You see, this is a 0.05 cubic feet per minute leak, and this air would be entering into this wall system, causing much more vapor to move into the system. In 30 days, you would have approximately 0.83 pounds per square foot, or 10 times, more than 10 times the water entering into that wall system. So that's a significant challenge, which indicates that sealing these interior environments, getting a good vapor seal, especially in this cold climate application, is very important. In a hot climate, the vapor movement is going to be the opposite. Defining a hot climate versus a cold climate really is a matter of, it's really under the judgment of the MEP engineer, but they're around the 40th parallel, 40th latitude in the US is about where these, the vapor movement will flip from a sort of a weighted average temperature and humidity index. So that's, of course, running through about Kansas. Maybe that line is moving a little bit north every year as global warming is incurred, but nevertheless, that's up to the MEP engineer to decide. So in a hot climate, we have vapor diffusion from the outside in. So this 90-degree temperature and 85% relative humidity would be moving inside to try and condition or change the conditioning of the interior environment at 70 degrees and 50% relative humidity. So that vapor movement is trying desperately to get inside the wall and cool down into a condensation on the inside of the gypboard. So gypboard is generally a faced product. It would have a paper facing on the backside, and what happens when water accumulates on the backside of paper facing, that equals mold over time. So it doesn't show up immediately, but it will show up over time if vapor has not been contained or addressed at this outside area. So permeability of your water resistive barrier in this condition is a very important factor to take into account. Over 30 days, it would be about double what it was in the cold climate application, and that would be 0.18 pounds per square foot. So air exfiltration, outside air moving in with the same CFM leak with these parameters would result in significantly more vapor moving into that wall system, which can then not exit. It would have to heat up significantly or have air moving through that system to actually help that water exit. So that water builds up as it condenses, and in 30 days, 2.8 pounds per square foot, or 15 times more water. Starting from a larger number, that is significantly more volume of water. So how much water is really a measurement of itself. The vapor diffusion here through a 4x8 sheet of standard gypsum board over 30 days would be about a third quart of water in this test, with a 1x1 inch hole drilled into a 4x8 inch sheet of gypboard would result in 30 quarts of water over that same period of time. So that is a significant differential, and really underlines the requirement for vapor retarders or vapor barriers. So buildings themselves function to pull in air and expiate air through the building structure itself. The stack effect, even though controlled within between floors in a commercial structure, can actually move up through a building core if air is allowed into that core, if it's not pressurized correctly. MEP engineers work compartmentalize the different environments within these buildings, and sealing the air movement between those environments will address a lot of the pressure differentials which are created by the stack effect. So basically, in summary, the stack effect is pulling cold air in through the exterior of the building and then beginning to create positive pressure in the top of the building as it tries to move back out. The wind effect is really from the primary direction of the wind, and you can see the pressure of the wind will change with the height of the building. Will create a positive pressure on the wind side of the building, and then on the lee side of the building would create a negative pressure or a vacuum, and this will create an air movement through a building through any gaps or leakages that can occur. Fan pressure and HVAC pressure is a designed element in the building, and frequently most buildings today are designed with about a 0.5 positive pressure to push air out through the building, but that may change. It may shift based on the zones created in the building and based on the designs of the HVAC engineer. This is important because you don't want to be pushing vapor from the building into the wall or vice versa. An additional element which needs to be accounted for, or at least be designed around, is wind washing. If you're in a high wind environment, the areas of the wall that are going to be receiving wind can actually, if there are gaps or gaps in the air barrier, that can actually allow wind into the exterior of the wall, which then moves through the wall system itself, especially with metal studs. With wood studs, not so much, but metal studs are open to some extent and can allow wind through the stud itself. And it will wash from the positive pressure side to the negative pressure side of the building. So basically mitigating the R value of the insulation in those corner conditions. So the effect in the interior environment would actually be a cold corner of that building, and that may occur as long as the wind is pushing against the building. So in buildings that get up above the surrounding environment, above 30 feet, that's where wind pressures really increase. It may become quite noticeable on the interior of the building. And so what is the effect of the leakage, air leakage in these buildings? Well, it can have multiple effects on the building over different time horizons. According to the National Research Council of Canada, air movement is the dominant factor in the transport of moisture through building envelope assemblies. So not diffusion so much as air movement. It is also an important component of heat transfer. So many problems concerning building envelope deterioration can be attributed to inadequate or failed air barriers. So degraded material performance, interior air quality, HVAC systems which perhaps were right-sized for the building could become compromised and could be undersized for the building with too much air movement. It's going to affect your thermal comfort and the air quality. This may also lead to moisture damage within the wall systems, wet insulation, which can start to affect energy efficiency. So it has multiple layered effects to the building performance. Common materials used to control the heat, air, and water that is affecting the building assembly start with exterior cladding. So that would be your either cement board, stucco, ephes, glass, metal, whatever system is on the outside, which is defining sort of the rain resistance or bulk water resistance of the exterior envelope. And then continuous insulation, be it rigid board or spray foam or a sort of a semi-board mineral fiber product can be used as continuous insulation on the outside. Building wraps, including mechanically fastened, peel and stick, and then liquid applied membranes can be used to keep create a drainage plane on the interior of underneath the exterior insulation and the rain screen. And then exterior sheathing. So this can have multiple uses in the building. Frequently the rain screen these days has multiple tasks, including being water drainage layer, as well as vapor permeability or impermeability as needed, and then of course structure. Your stud cavity insulation is the next line of defense for thermal transfer, and that can be unfaced or faced. And then plastic sheathing at the interior, polyethylene, could also be craft-faced bats for residential structures or wood frame structures, and then interior gypsum board. So this has, gyp board has its own characteristics which are beneficial to the building envelope, but it is vapor permeable to some extent unless it's covered by wall coverings or paint. Wall coverings, if they are plastic or textile based, may actually function as very effective vapor retarders, whether they're designed to be so or not. So if you have vapor movement from the outside in and you have a wall covering, be aware that that is functioning as a vapor retarder and will perhaps and simply needs to be taken into account from an envelope perspective. So let's move on into thermal movement or thermal performance of wall systems. Heat moves through a wall system through three functional elements. The first being conduction. This is heat transfer by basically physical contact of the materials. the molecules vibrate faster in a warmer material, and then we'll communicate that to a colder material. So the conductivity and the ability of the molecules to get excited by the juncture of these other molecules is what causes that conduction. Convection is the next method of movement for heat, and convection is really the tendency of cold air to fall, warm air to rise. Conductivity is also is basically taken into account with the cold air. When it's falling, it is actually touching along a colder surface, and that conductivity is conducting to the air and causing the air to cool and then fall. So warm air, when it is warmed by either radiant or conductivity, starts to rise. So this movement of air needs to be controlled within the wall cavity so that it doesn't actually form these convective loops. The final method of heat movement is radiation, and radiation is generally defined as what if your hands are out to a campfire, they're going to be quite warm. Your back, however, is going to be quite cold. So this is radiant heat transfer. It's also what makes the sunlight feel so good on your face in the spring. And but there's actually no physical. It's really a transfer through wave rather than through conductivity or through convective loops. So this radiant transfer is the most difficult to see in a wall system, but it does have a dynamic effect. So in summary, it's a dynamic movement of heat, which we're trying to control for within your wall systems. The radiation, convection, and conduction all work together to try and defeat the purpose of separating the interior from exterior environment. So in summary, the challenges that are trying to prevent the optimal performance of your walls would be water penetration of any sort, controlling the movement of water, and then the transfer of moisture through air movement, air infiltration and exfiltration, wind washing, and then heat transfer via conduction, convection, and radiation. So let's look at sort of a standard wall system. This would be a uninsulated wall cavity, sort of like the Irish church, where there's actually no air leaks, but there's no insulation to control the thermal transfer either. So most of the transfer of energy through these systems would be by radiation. The next amount or bulk amount of thermal transfer would occur through convection or convective loops that are set up inside these walls. Cold air cooling along the outside and then warming along the inside. If we add insulation to this cavity, an insulated wall cavity with no air leaks would reduce its thermal transmittance by about 75 to 90%. So depending on the thickness of the wall and the amount of insulation that's being used. The most notable function that's being compressed is suppressing these convective loops that would be established inside of an uninsulated cavity. And that reduces the amount of conduction. So once those convective loops are suppressed and the radiation is controlled by the broken up fiberglass strands of a fiberglass insulation, at this point, the remaining 10 to 25% of thermal transmittance would be through conduction or radiation. So conduction would be 75%, and that would be through, let's say, metal fasteners that go into the exterior of the wall, and then radiation would be the remaining amount. So let's talk a little bit about what is the latter amount of how to control that last amount of thermal shorting or a thermal transfer that is occurring. So the conduction is defined as either thermal bridging or thermal flanking, and that can either be through studs, let's say metal studs within the wall system, or through fasteners, which penetrate the sheathing of the wall system and then create thermal shorts. So how to reduce these thermal bridges is really where continuous insulation comes into play. It can degrade wall performance by 40 to 60% on average. You see in the photograph, the thermal image to the right, that about 25% of the wall area of this stud-framed house is functioning as a thermal bridge. So the most common offenders would be your steel framing, of course, which is a conductive material. Balconies, which are generally concrete balconies, slab edges, and then window frames. Adding exterior insulation to this thermal image, you see a lot more of the heat being controlled and the thermal bridging being essentially stopped. So what are the methods, the primary methods of continuous insulation which reduce this thermal flanking or thermal bridging? There are three primary elements that can be used as exterior continuous insulation. And those include rigid foam board, and this can be a polyiso or a polystyrene product, faced or unfaced. And these can have other characteristics about them. Facers can add specific characteristics to be also used as water drainage planes and as impermeable barriers. Spray foam itself is another good option. Want to be careful that you use only closed cell spray foam in these applications. Open cell spray foam in this environment can act like a sponge. Of course, it isn't left exposed generally, but to make sure you get the water drainage characteristics, closed cell is going to be the primary option for exterior continuous insulation. Mineral wool would be the final, and in some instances for commercial, perhaps the most optimal type of exterior continuous insulation. Has a lot of great characteristics, the primary one being it's almost completely non-combustible. We'll look into the different characteristics of these materials in the next few slides. So let's look at a comparison of these characteristics, and this will affect the design of the wall system itself. Polystyrenes are here on the left. Polyiso and the polyiso and the polyurethane spray foam are right here in the middle, and then mineral wool is on the right. All three have pretty distinct characteristics. EPS is the most cost-effective, and so perhaps has the least amount of valuable characteristics for an exterior system. As a drainage plane, it would definitely require tape, usually, actually always. EPS is unfaced. XPS as well would be require tape. Sometimes XPS products are able to be faced. Both of these can be used below grade. As a vapor retarder, they are somewhat permeable, but still function fairly well to retard vapor. EPS is not technically an air barrier, but XPS can function as one with tape. The R values are about 4 inches per inch with EPS, 5 inches per inch with XPS, and the densities, which are not shown in this chart, are different for EPS and XPS. The primary differentiating characteristic is the melting and liquefying, the fire performance of these products. These melt and liquefy at much lower temperatures than the other three products on the chart here, softening at about 165 degrees and then melting at 200. Polyiso and polyurethane spray foam have these other characteristics. Polyiso can still function as a drainage plane. Both of them are very impermeable. They function well as vapor retarders. Polyiso can be a vapor barrier. class 1 vapor barrier. Polyiso with a facer can also function as an air barrier, and the R values per inch are higher for polyiso and spray foam than for all the other materials on the chart. And the other characteristic which is helps define these plastics as different than the polystyrenes is how they react to fire. With polyiso and with basically polyiso is a description of the plastic. Polyurethane is the spray foam. They both char, but they do retain their shape. So they don't actually turn back into a liquid and then catch fire. That's very important for the performance of these characteristics in tested assemblies. Mineral wool is completely non-combustible. It's not a drainage plane, although it can be treated with silicone and give it water repellent properties. It can be used below grade. It's intended to be completely vapor permeable. It's not an air barrier, and it has a decent R value per inch, the primary characteristic being that it is non-combustible. So let's look at these wall systems and how they respond to having continuous insulation. In a cold climate, as we've seen before, the vapor is moving from the inside out during the winter. And so you would see the condensation on the backside of the sheathing in this application. With continuous insulation, that thermal saturation point would generally not be reached inside the wall. It's been moved outside the wall. So even if it's collecting on the backside of this exterior continuous insulation, simply adding a weather barrier here to the face of the sheathing would be sufficient to ensure that saturation point or condensation is not occurring. So from the CI inward is now conditioned space. So looking at this in terms of the delta, the change in temperature, without CI, most of that delta of temperature is occurring inside the wall cavity itself, which is exactly where you don't want it if you're going to have vapor transfer. With CI, simply 1.5 inches of polyiso or 2 inches of polystyrene, you would have most of that delta occurring in the outside of the building envelope, which is where you want it to occur if there's vapor in the air. In a hot climate, of course, the inverse movement of vapor collecting in the inside of the drywall, exactly what we want to avoid. With the addition of conditioning or exterior continuous insulation, that vapor, if it does make it through this facer, the delta, the condensation point is going to be hopefully right here at the outside of the wall system. This would be with the correct amount of exterior continuous insulation, which is perhaps code plus from a code standpoint. So this conditioned space from the inside is forcing the condensation to occur in the outside of the building envelope. So inverted, looking at the delta of temperature, the temperature is moving down from the inside to the out here, and most of that delta would be occurring from the higher heat areas on the outside here to the conditioned temperature in the inside. This temperature gauge is actually a little off. You would be trying to maintain at 70 degrees generally in the inside, coming down from perhaps at 95 on the outside. So to review our learning objective, we talked about how insulation is mitigating these challenges of heat, air, water movement through walls. Talking about obstructing the process of conduction and radiation, suppressing air movement with convective loops through insulation on the inside of the wall cavities, and then raising the temperature of the interior materials, moving the conditioned space to the outside of the wall system. And then we talked about how we are reducing the thermal bridging and thermal flanking, which can occur without continuous insulation. So let's shift gears again and talk about sound transmission. Just a couple more concepts to cover here, sound transmission as well as fire. So these are two things that we're asking our wall systems to do, in addition to vapor control, structure, air, water, heat, transfer control. So with sound, generally you're trying to achieve a transmission loss unless you're designing a acoustical space, in which case you're trying to reflect sound and add a certain amount of reflectivity. With transmission loss, you're simply trying to reduce the amount of sound transferring through a wall system. A measurement of that from a system perspective is your STC ratings, and that again is for the entire system, and assuming that it's not being compromised with thermal flanking or other gaps in the wall system. A measurement of materials themselves is called an NRC, and we're most familiar with that with an acoustical ceiling tile, would have actually an NRC rating applied to the material itself. So again, an STC rating is an assembly test. It's done in a laboratory, which is a controlled environment. It's a single number, which is measuring transmission loss for 125 to 4,000 hertz, and this is intended for speech and music, which is really where that wavelength occurs. A different measurement of a system would be an outside-inside transmission class, and that's an OITC rating, and that is better for transportation noise, 80 to 4,000 hertz. So these graphs right here indicate what the perceived effect would be for an STC of 30 through 60. If you have amplified sound, somebody blasting their speakers in the adjacent room, an STC of 60 would be required to reduce that to nullify that the perceived sound. Every 10-point increase would be perceived in STC would be perceived as 1/2 the amount of perceived sound. So that's this 9 to 10. This would be perceived twice or half as loud. An STC of 40 would be required to be perceived as a 95% reduction in sound transmission. Most code requirements are for STC of 50 between multifamily units, and in a field verified application that would be allowed to fall to a 45. There is frequently a 5-point loss between the tested assembly in a lab and the built tested assembly. So what we see on the chart here is structure-borne vibration is down here on the lower end of the frequency range. Traffic noise can move through the entire range of frequencies, and then the standard, ballast, light noise, HVAC noise, speech, would all occur in the STC range in the 125 and above. So common exterior wall assemblies would result in these ratings right here, 2x4 framing at 40, an OITC of 25. So you see the reduction between the STC and the OITC. The best system here would be a masonry or mass wall of masonry and precast or CMU, and that would lend itself to a 50 to 60 STC rating and a very comfortable OITC rating of around 50. A couple of points in this slide to note. One would be the differential between closed cell spray foam, which has a lower STC if it's filling a cavity, versus fiberglass, a combination of fiberglass and closed cell, which would increase the STC rating. Other elements to note here are mineral wool is actually resultant in a higher STC rating of 44, so you gain 4 points over standard exterior CI. And then polyiso itself in a roof system is generally not considered an acoustical element. You see here with 1.5 or an additional 3 inches, you still have an STC of 27. Mineral wool is, of course, acoustically a little better than, let's say, blue board or foil facer behind a rain screen, so something to be aware of, that there can be some visual interference with different materials. So to summarize our acoustical elements, we've got a higher STC rating, or OITC would mean less sound transmission. Adding weight, mass, cavity insulation, or vibration breaks are good ways to control the movement of sound. Make sure that you design your wall system to include your doors and windows, otherwise leaks or unsealed connections will defeat the actual assembly in the field. So the last element we wanted to cover was fire control. What is fire control trying to do? That is trying to give the occupants more time to exit or egress from a system. In multi-story systems, this is even more important to allow time for egress. With non-combustible construction types, it is important to make sure that egress timing is allowed. This is where NFPA 285 came into effect, is for these type 1 through 4 structures, which are designed to be non-combustible. So a test was developed and has been in place since the 80s to basically test the exterior wall assembly to make sure that it is not catching fire and communicating fire from the inside along the outside of the building to adjacent spaces. The test runs for about 35 minutes, and the assemblies cannot catch fire on the inside or the outside of the assembly and transfer that fire. Every time you introduce a combustible element to a wall assembly, there needs to be a test or some sort of approval and engineering judgment for that, how that combustible material is going to affect the assembly. Combustible claddings, including plastic EFIS, polystyrene specifically, foam plastic insulation, and the various code or chapters are listed here. So not all materials, continuous insulation materials, are made equal. Fiberglass and mineral wool are not considered non-combustible. Respectively, fiberglass will melt at 1200 degrees, mineral wool at 2100 degrees. So the rest of the building will be completely engulfed in flames by the time those begin to melt. Thermoset materials, be they polyiso or spray foam, are better than the thermoplastic materials, but they are not completely non-combustible and therefore need to be tested and need to be part of a tested assembly in commercial construction. Thermoplastic materials are among the worst performers in exterior wall systems, and indeed are the ones that caused the requirement, triggered the requirement for NFPA 285 testing. They soften at 165 degrees and melt at 200. So to review, the requirements for fire and sound are different based on the goal of the tested assembly, whether you're trying to control sound or you're trying to amplify sound. They're all affected by the height and the design of the building. Combustible materials in non-combustible assemblies do require NFPA 285 testing, and approved assemblies are available with polyiso and SPF, excuse me. OITC ratings are a better measure for exterior wall systems for acoustical ratings, and then adding weight or mass or fibrous insulation are good ways to control acoustics. So we're asking a lot from our exterior wall systems and interior wall systems for acoustic perspectives and fire. We're asking them to control fire through, through water, through bulk water, vapor, etc. We're trying to mitigate the effects of air leakage and wind washing, control the transfer of heat, and then, of course, control sound and fire with these systems.
Great, thank you so much, Dwight. Before we dive into our questions, I do want to go through a few additional resources. First and foremost, Coming up next are our next webinars in our AIA Certified Webinar Series. On the 23rd, next Thursday, we will have Architectural Acoustics. And then on the Thursday after that, we will have Continuous Installation on April 30th. So please join us for those. In addition to our upcoming webinars, we do have an online resource for anybody who's looking for either architectural support or even just building support, and that is Tech Connect. And next slide, please. Tech Connect is basically our online resources for architects, for building, for installation installers, for architects, for anybody who's looking for additional support from an actual person. And so you can actually contact this group through that phone number, 1-800-654-3103, or you can email our specifier services team, and that's bispecservices@jm.com. We also have our JM SmartBinder app, and this is an app you can download to your phone where you actually have access to all of our technical documentation for all of our products. This can be really handy if you're in the field or if you just need quick access to JM data sheets, SDSs, that sort of thing. So go to the Android App Store or the Apple App Store, and you can search JM SmartBinder and download our app directly to your phone. It's free of charge. We also have a Continuous Installation Solutions webpage. So this is a webpage that has resources for all of our continuous installation solutions. You'll be able to compare our products side by side, and that is jm.com/CI, as in continuous installation. Also, our webinars are going to be recorded on demand, as is this one today, and you can find these on our website. If you go to our BI Building Installation page, you'll find it, the webinars link for our webinars on demand on the left-hand column there. Just click on that, and it'll take you directly to our webinars where you can watch them, share them with colleagues, that sort of thing. The AIA certified webinars are not currently available for certification if you watch it on demand. So you do have to attend the live webinar currently to get your certification for attending the AIA certified webinars. And finally, a certificate of completion for everybody who attended the live webinar today. We will submit a certificate of completion. If you registered with your AIA number, we will submit that for you to AIA. We'll record it for you. If you do not register with an AIA number, you will receive a certificate of completion in your inbox on Monday, April 20th. So with that, we're going to go ahead and move on to some questions. Dwight, the first question for you is, what do you recommend for testing wall infiltration integrity?
So testing of wall infiltration integrity, assuming that's air and vapor infiltration, can be done through either a humidity measurement device and also really through air pressure differentials between the wall and between the exterior and the interior of the wall system. You want to be testing inside the wall system rather than simply from one side to another. And this should definitely be done in the field if possible. Of course, it's difficult to do in a mock-up, but it can be done in controlled environments as well.
Great, thank you. The next question is, how can insulation effectively be used to mitigate thermal bridging through wall assemblies?
Thermal bridging is usually a result of thermal transfer through various penetrations of a wall system, be they metal or concrete. Obviously, cladding the outside of these materials or continuous insulation is the primary methodology, but you want to make sure that you're also creating thermal control or thermal separation between these exterior cladding systems. So if you're using Z-furrings on the exterior, you want to make sure you're using some sort of ceramic or some sort of device which separates the thermal transfer from the interior of the building with that new assembly that's holding up the exterior CI.
All right, thank you. The next question. The difference in how to insulate based on your specific climate. I'm in a mild marine climate. How does that differ from a dry or more extreme climate? And where should I place the insulation?
So in a marine, well, your HVAC engineer is going to be the best for providing a model of how to, where to place the insulation in a system. In milder environments, insulation is honestly not as critical. If your temperature outside is 70 degrees and your temperature inside is 70 degrees, really at that point you're trying to simply make sure that the humidity keeps from moving inside the wall. So the R value of the insulation, where that dew point is still important, and so really at that point it would become where's the highest amount of vapor in a marine environment. It's going to be moving from the higher vapor exterior to probably the lower humidity interior. So in that condition, vapor barriers especially would be placed on the outside and continuous insulation.
Great, thank you. The next question is, how can you test for moisture or mold in the wall after it's 2 to 10 years old, and what's the reasonable testing time?
So the best time to test is after the wall system has been conditioned. Normally, well, at least in northern environments, the time to test is when the humidity is higher on the inside and lower on the outside, and then you would test inside the wall system with humidity or relative humidity testers. And then you would really what you're testing for is leakage of or transfer of that humidity to the interior of the wall system. For the other environments, you would want to test in the middle of summer. You want to test when it's higher heat, higher humidity in the exterior of the building and lower on the interior. At that point, looking to make sure that there's not higher vapor in the interior of the wall system as it's trying to move in toward the lower humidity interior environment.
All right, thank you. The next question is, it looks like wall assembly integrity and design is very climate zone specific, even possibly the sun orientation of the exterior wall. Is that correct?
It is definitely climate zone specific. There are 8 climate zones in the U.S., ranging from the tip of Florida and Miami up to Alaska at climate zone 8, and then across the U.S., different humidity zones, marine environments on the coast, and then drier in the western part of the United States, and then east of the Mississippi, more humid environments. These all affect the design of the wall system, and by that, the reason they affect the design of the wall system is because they are the temperature is making the humidity move in different directions. So even sun orientation, and I'm glad they brought that up, the sun orientation can obviate the need for elements of vapor control, but it can also cause expansion and contraction of the materials on the outside of the building, which could actually mitigate some of the adequacy of those systems and how they're attached. That you want to make sure to take into account that differential movement, any solar gain, but vapor, in a higher heat environment is really just transferred back into vapor, so it doesn't have a chance to condense.
All right, the next question is, what would be a good fix for an existing townhouse common wall that has sound transmission happening between?
So sound transmission, the first line of defense is going to be filling the cavity, and assuming those cavities are already full and you can't add a secondary wall to it, probably the most cost-effective way would be to add resilient channels to the wall system on the outside of the existing drywall. So you can add those channels and then add another layer of density of drywall. And depending on the thickness of the channels, it may be wise to add either mineral fiber or fiberglass insulation in between those channels under the new drywall as well.
All right, what about insulating buildings with lots of glass?
Glass is a fairly decent insulator. It's really the thermal transmission of the frames, which is more more important, that there's lots of different types of insulating glass with different characteristics. And then, of course, there's coatings you can add to the glass, which reduce the amount of radiant heat transfer. But the frames themselves need to be thermally broken to affect proper heat mitigation or transfer mitigation in the glazed systems, if they're either curtain wall or storefront systems. And this basically means that the frame is two separate pieces separated by either an airspace or ceramic pieces that control the amount of heat that are moving through those frames.
All right, thank you. The next question is, what do you suggest on insulating load-bearing masonry, brick and/or block, wall that will have a new exterior metal composite and metal siding installed over this masonry? It's a two-story building constructed in the 1970s with no interior insulation, located in a northern climate.
Okay, so that's very specific. So insulating a load-bearing masonry wall, which means it's going to be reinforced masonry, brick and block. So the cores of the brick and block are filled already with a reinforcement. So at that point, really, there's only one option, and that's going to be continuous insulation. The question is, where do you place the continuous insulation, on the inside or the out? If this is going to be occupied space, you would probably place it on the exterior of the building to condition that wall system from the inside out. Although you can also place it at the interior of the building. Continuous insulation will work in both locations. The masonry is going to be holding a bit of heat and mass, so if you're allowing it to heat up and cool down, that could cause condensation in the inside of interior insulation. So again, this is probably pointing towards exterior continuous insulation.
Great, thank you. The next question is, can you please address interior insulation and masonry window opening insulation continuity for existing historic double or triple wide brick walls?
So interior insulation and masonry window opening insulation continuity. If you've got a double or a triple wide brick wall, it means you have an airspace, which is already affecting the performance of that wall and increasing the performance of the wall. So that continuous insulation is definitely going to need to be on the inside of the building. So adding framing or some sort of furring will address the aesthetic, I guess, on the inside, but it will also definitely assist with the thermal resistance of the wall system. So the continuity is obviously going to have to run up from the interior of that building envelope, run up the side of the wall, and then transfer into an insulated ceiling or roof system.
All right, thank you. The next question is, does the temperature differential between a building's interior and the ambient exterior influence the direction in which moisture travels?
It definitely can, depending on the environment. So we've talked about the northern environment where vapor and temper differentials are really to be measured in the middle of winter with higher humidity on the inside, vapor moving to the outside to the colder where it's going to condense. Inverted about south of the 40th parallel, especially in summer conditions, higher humidity on the exterior, moving in towards the cooler interior where it's going to condense. This can also be different in a, let's say, a desert environment. So in the desert southwest, you may have higher humidity at the interior of the building, colder temperatures, and then lower humidity and higher heat in the exterior, in which case that humidity is going to be moving from the inside out. So it definitely is temperature and condition dependent. So it's got those two variables, the temperature and where the highest humidity spaces are. So humidity is going to be, or vapor is going to be moving from the higher humidity to the lower humidity in every condition.
All right, thank you. The next one is for a mass wall of CMU, what qualities do you look for in a building insulation board?
So with CMU, you could, for that application, you could use any one of the different types of exterior CI materials. If you're looking specifically at board products, of course, you're talking about polyiso, polystyrene, sometimes a mineral wool board, which can be sort of a semi-rigid board product. Honestly, it depends on what you're looking for with the application. That's going to be the critical detail. What else are you asking from that exterior continuous insulation? Is it going to, do you want it to function as a vapor barrier on the outside, in which case you would require a polyiso or a XPS polystyrene, or even a spray foam material, which would be a vapor barrier on the outside. So that would really rely on what other characteristics you're looking from the material itself.
All right, thank you. The next question is, what are the new, or if any, challenges to building envelope wall design for 2020 and beyond?
Well, we've talked about continuous insulation, which was introduced as a code requirement. Currently, the movement is more towards, let's say, condensing the amount of labor required to install these materials, in which case you're asking materials to multitask. There are, we've talked about the different types of board products. Some boards function as multiple tasks. Let's say an insulated wood board or OSB board, which has the insulation attached, that would require less labor to install and would add structural and insulating characteristics. A polyiso with a foil facer and a taped facer would function as multiple elements, including a water drainage plane, vapor barrier, and insulation. So it's really a matter of simplifying the production process of installing these materials and asking for more from each type of material.
All right. The next question is, how can I be certain all of the elements in a wall system are compatible with each other, such as an air and water resistive barrier and SA flashing?
So compatibility is really a tested phenomenon. So I think in the specifications, that's going to be the best place you're going to address compatibility. There are systems that are designed to go together and they're marketed, but there are other less costly systems which will still work together. Pre-construction testing is where most of that is resolved, and that can be written into the specifications.
All right. The next question is, there's an existing masonry wall and a two-way slab building that we will be exploring retrofit insulation options on. It would appear that the best potential option with regard to overall cost is to insulate the interior wall rather than the exterior. How is it best achieved in retrofit to prevent moisture within the interior construction?
So again, we want to look at which direction vapor is moving. If you are concerned about vapor moving from the outside to the inside of the structure, which can definitely happen with any type of masonry materials, you'll want to pre-apply some sort of vapor retarder, even if it's a thick class 3 vapor retarder paint to the masonry itself prior to the installation of the continuous insulation at the interior.
All right, great. The next question is, what type of wall assembly would you need to build to achieve an air leakage of 3.0 ACH or less?
Well, that really air leakage is going to be a function of the air barrier. And air barriers can be applied on both sides of the wall or simply one side of the wall. Both will functionally address air leakage. If you're measuring, it depends on what you're measuring. If you're measuring on the other side of the wall from the air barrier, you may have a little bit of movement from other locations in the wall, but that's really about the installation and the type of air barrier that's being used. So that measurement would basically default to the the installation and the characteristics of the air barrier being applied.
Great, thank you. The next question is the term rain screen essentially just another name for veneer?
I think with veneer, there's more of an aesthetic characteristic. There's also, a brick veneer versus a rain screen material. Both are essentially the same in their function. The rain screen would be a system that's attached with an airspace underneath that is designed to simply vet or move bulk water along the outside of the building. And the same thing with a veneer. Technically, I guess they function the same in terms of their attachment and having the cavity behind them.
All right, next question is, most regions are both hot and cold climates depending on the time of the year. How are wall systems supposed to satisfy both?
Well, any MEP engineer will tell you that at some point during the year, you will have the highest vapor flow that the wall system is going to incur versus other types of the year when it's 70 degrees, when the humidity is the same inside and outside, or the temperature is the same. You're going to have much less pressure differential. You need to design for all of those elements, and that's why two elements are critical to that design. One would be the vapor barrier on the primary side of vapor flow, and then moving the exterior insulation or attaching it to the outside of the building so that the interior of the wall becomes conditioned space.
Great, thank you. The next question is, how do you treat vapor transfer in climates that have a mix of hot and cold days throughout the year? No vapor barrier?
Rarely would no vapor barrier be the primary solution. With the same question as before, you're going to have vapor flow higher at certain points at some point with a standard wall system. You will have the condensation point or the dew point somewhere in that wall system. True about roof systems as well. What we're trying to do is keep the vapor out during those at that point. So the vapor is not allowed to enter into the wall system and condense. With the addition of the continuous insulation, changing the delta of where that temperature differential is going to occur, we're effectively addressing it from two different angles. One is from the temperature perspective, and the other one is from the vapor control perspective.
All right, thank you. The next question is, backing up slightly, is there a difference between saturation point and dew point?
Not really. Saturation point is where the air is completely saturated and will turn into condensate, which is from the lay term called the dew point.
All right. Is it accurate to conclude that if you control air movement, then vapor and moisture control are a byproduct and need not be as concerning?
Oh, this is a critical point. Vapor is completely different from air movement. You can have air barriers which are vapor permeable, which means vapor will diffuse through the air barrier, and this is a design function. If you want whichever side of the wall you want to be vapor controlled, or is advisable to be vapor controlled, those would allow vapor permeability, but at the same time can restrict the movement of air. So Tyvek is an excellent example of this type of function.
All right. The next question is, what is the current thinking on where to place the air/vapor barrier in conditions where you have both heating and cooling cycles?
There's a rule of thumb. Of course, this is going to be the ultimate decision lies with the mechanical engineer and their modeling. But where is the primary, I guess, where's going to be the weight of evidence in terms of vapor movement. In a north Midwestern environment, you have a median January temperature of about 30 degrees and a humidity of about 40%. So in those environments, your vapor is going to be moving from the inside, the conditioned environment, to the outside, which is lower vapor and lower temperature. And the reasoning behind this is you want to make sure that vapor does not condense inside the wall system. Of course, as you move south of the 40th latitude, at that point it may flip, and so you will not have that lower temperature in the median temperature in January, and most of that moisture movement will be from the outside to the in. So you want to the ultimate goal is to reduce the condensation inside a wall to nil, and so that's going to be the deciding factor of where that vapor barrier is placed.
All right, the next question is, what are your feelings for the best insulation to be specified in historic buildings constructed with a brick stud wall system with tar paper or felt as the building wrap?
So the best type of insulation for historic buildings, well, besides the aesthetic effects, brick and stud wall system with tar paper as a building wrap, the tar paper is vapor permeable. The brick and stud wall systems, the brick would really require a continuous insulation applied to, well, depending on where you need the aesthetic of the brick, and depending on where the building is located. If you're in a southern environment, you may want to put that on the outside of the building. If you're in a northern environment, maybe on the inside of the building, just as vapor control as well as conditioned space, where you're putting that conditioned space. Of course, with the framed system, you can put it inside the framing. Really the location of the building is going to define where you want to put the vapor retarder in that system, but the insulation would be in one of those two locations.
Okay, the next question is, does a vapor barrier on the inside behind the drywall cause moisture to collect and get trapped?
And I think the latter part of that question is inside the drywall itself, and yes, it does. So there's two things going on with drywall. One is that it generally, paint and primer is recognized as a Class 3 vapor retarder, and acrylic or latex paints are very specifically designed to provide a coating to that drywall. So this limits some of that diffusion through the drywall from a sort of a functional standpoint. And then drywall is really designed to be able to increase humidity and decrease humidity without affecting the system unless it freezes. So drywall will be able to resist this humidity differential or delta over the year. But what we're trying to do is keep the vapor from transferring through that drywall and into the wall system, where it can create much greater effects on thermal insulation if it condenses. So yes, a polyethylene or even craft asphalt treated craft paper vapor barrier can be a significant benefit to the reducing the vapor flow through that wall system.
All right, can you speak to the best envelope details to prevent ice damming?
Well, ice damming frequently will occur where in a roof system, let's say it's a residential system, you've got a sloped roof, maybe a 3 to a 12 pitch, and the water heats up either through UV on asphalt shingles or through heat transfer through the insulated attic space, and then will refreeze where there's no longer any heat transfer. So usually that would be the eave of the building, and so couple of ways. In eaves, normally it's addressed from sort of a ice melt standpoint. But if you could actually heat the eaves to some extent, and that would be running. Well, let's see. That would be a detail to be worked out on how to make sure the eaves remain heated. Although that would be a conditioned attic space. So a couple of things going on with that. Really, you'd kind of have to look into it from a sort of a case-by-case perspective. If it's happening on an existing building, you may the way to affect that may be to increase the amount of insulation to the proper level, R50 in the ceiling system, to make sure there's less heat transfer occurring, so it actually doesn't melt and flow off the building.
All right. The next question is, what is your opinion of film products that are used to improve the quality of heat transfer of windows, as well as the protection of interior surfaces from ultraviolet rays on windows?
Well, those need to be evaluated. Some are better than others. 3M obviously is an excellent manufacturer with good quality record. Depending on the intent of the film product, you'll have different performance characteristics. The most common film product is the solar control or low E film product. But the other, more reflective types can reduce more of the radiant energy absorbed from the sunlight. The application, of course, is very important with these and where it's applied in the window assembly itself. Some that are applied after the fact or can become compromised through condensation and other elements. So this really is part of the original design intent and getting it on the correct pane or side of the glass.
Thank you. So the next question is, how much do door or window openings affect STC of an exterior wall?
Significantly. If you have, let's say, the masonry wall that we discussed in the presentation, and it has an STC of 55 in a tested environment, and it is constructed with a door system with an STC of 30, and the door is not properly sealed, so it has thermal flanking occurring, your STC rating of the entire wall system will drop by 10 to 15 points. So it's important to make sure those details, the connections between the walls are sealed properly to maintain the design intent of the STC rating.
All right. Is there a calculation for how much the STC of a wall system increases as the material thickness increases? As in, if you went from 4 inches of mineral wool to 8 inches?
There is a calculation, and that is based on the STC rating of that system. So you'd have to look at the thickness. The assemblies are available online through the various manufacturers. Usually for that question, it would be an insulation manufacturer that would have a 4-inch versus a 6-inch assembly test. Or 8-inch, excuse me, 4 to 8.
Fair enough. The next question is, do the ceramic insulation coatings work? Some companies claim to have an R value equivalent of 16 to 20.
I'm unfamiliar with ceramic insulation coating in this application. I know that ceramics are good for eliminating thermal transfer of exterior cladding systems for the attachment mechanisms. I know that ceramic itself is an excellent coating for glazing, for spandrel glass, but just depending on the characteristics of the specific material would define whether or not it is working as claimed. One thing to be aware of is the claims on manufacturers' data sheets. Make sure you look for tested values versus typical values. So that's just a finer point of language, typical value can be optimized, shall we say, versus a tested value, which is actual.
All right, the next question is the flame spread you mentioned in the presentation for closed cell insulation, does that include 1/2 inch gypsum board? In an unoccupied space on a below grade existing masonry foundation wall, is drywall required on the closed cell insulation?
So, okay, so with every spray foam or plastic product, a thermal barrier is required unless it meets certain factors in unoccupied space, let's say an attic or a crawl space in a residential building. That is, if it meets certain criterion, which are listed in the IAPMO reports available from various manufacturers, that a thermal barrier would be required, and that could be either gypsum, could be a board. There's multiple products that can be used. 1/2 inch gypsum is the most common, but in those conditions, unless it is specifically meets those conditions, it will require some sort of ignition barrier in those spaces or a thermal barrier in commercial spaces.
All right, the next question is, I often see walls with multiple claddings, possibly yielding multiple insulations, AWRBs, assemblies, etc. Would you agree that all of these different wall assemblies need to be evaluated independently for their overall impact on the building and then also create multiple NFPA 285 assemblies?
Absolutely. Every exterior assembly, which includes for a type 1 through 4 building, which includes combustible elements, will have to have an NFPA 285 assembly in order to qualify to be permitted. Characterizing these assemblies, including multiple assemblies on exterior of a building and these types of buildings is one of the challenges of architecture currently, and making sure that they are constructed as they must be according to the assembly test is the other challenge. So if there is a differential between the built assembly and the designed assembly, that's where an engineering judgment would have to be entered, and the engineer at that point is taking the risk of the performance of that assembly.
Thank you. So the next question also pertains to NFPA, and that is, does the transition of one NFPA assembly to another need to be tested?
Oh, that is an excellent question. Need to be tested versus required to be tested being two different things. I think it should be tested, similar to any other detail that, where you're trying to accomplish a certain thing, whether it's water control, vapor control, etc. Whether it's required to be tested, at this point, I am unaware of a requirement for testing of the joints between NFPA 285 approved assemblies.
All right, the next question is, there was a slide showing 3 buildings. One was an older building, 100 years or so. How is a retrofitting handled to limit or even omit thermal leaks?
So a retrofit to eliminate thermal shorting or increase the R value of those buildings would have to be applied to the interior of the structure. So continuous insulation can be placed to the exterior or interior of the wall. And at that point, to eliminate the aesthetic effects of putting it in the exterior, you'd have to put the CI on the interior. So at that point, the conditioned space is really just inside of the wall system. You're not conditioning the wall itself. So ideally, your vapor retarder is on the outside of that wall cavity.
All right, the next question is, how effective is canned spray foam as an insulation for both heat and sound? For example, if it were to be used between 2x4 studs and polyiso board.
So spray foam works well in conjunction with other materials as a tested assembly. Canned being, I assume the cans you get at Home Depot, but polyurethane closed cell spray foam does not have the highest STC ratings in the tested assembly. So a combination of fiberglass and closed cell is going to give you the best results.
All right, and our final question is, in an EFIS system, they're creating a drainage plane on the backside of the rigid insulation with rows of sealant. Doesn't this negate the continuous insulation values by allowing air, heat, cold, and vapor to pass between the insulation and the sheathing?
I guess technically it would, but the consequences of not including that would be more difficult to mitigate than including it. I've seen the details for that type of assembly, and we did look at the characteristics of EFIS or EPS as an air barrier, and it does qualify as an air barrier. Technically, I think the way those are detailed, wind-driven rain would be the primary element, as I don't know that they're open at the top. They are open at the bottom to allow the water out, but I'm not sure they're functioning as a rain screen so much as simply a water drainage plane, which can also be accomplished with 2 layers of WRB.
All right. Well, Dwight, thank you so much for your time today. We certainly put you through your paces with all those questions, and we appreciate everybody who attended. And your certificate of completion will be in your inbox by Monday, April 20th. And we all wish you the best of luck and have a great weekend.
Thanks, everyone.